Now you can start. So we want to welcome now Dr. R. Weglein. So go ahead.
Thank you, Osvaldo and Sergey, for this opportunity. The title of the talk is Multiple Signal and Noise. There are two views of signal and noise. One is that primaries of signals are signaled to be migrated, and multiples are noise, and that's called the exclusive view. There's another view, which is called the inclusive view, that primaries and multiples are both signaled to be migrated and inverted. We hear statements these days that we are no longer removing the multiples and migrating the primaries. We are now migrating primaries and multiples. The purpose of this talk is to examine this exclusive, inclusive viewpoints and see where we are and where we might be going. Okay. Maybe I swallowed this. Is that better? Okay, good. Since migration is a key to the issue of whether multiples are signal or noise, let's say a few words about what migration means. Wave theory methods for migration have two components, a wave propagation component and an imaging condition. John Claerbout, in 1971, and in that era, made three landmark contributions to imaging conditions. The first, the exploding reflector model. The second, time and space coincidence of up and down going waves. And the third, predicting a source and receiver experiment at a coincident source and receiver subsurface point and asking for time equals 0. Imaging condition 3 defines wave equation migration, and imaging condition 3 has standalone capability compared to imaging condition 1 and 2. All current RTM methods are imaging condition 2, not 3. To convince you, if you need convincing, of the difference between imaging condition 2, which all current RTM methods represent, and imaging condition 3, the predicted source and receiver experiment. At depth, I suggest you look at a single interface, homogeneous overburden, give yourself a perfect shot record, analytic data, and take the time and space coincidence of bringing the wave back and the source field forward, and compare that to what you would do for a single shot record using Claerbout's imaging condition 3, which is predict what an experiment will do, a coincident source receiver experiment will do at time equals 0. The first, imaging condition 2, will give you no consistency of reflection across that single interface. I'm talking about perfect data. In contrast to Claerbout's imaging condition 3, which will not only give you a consistent, it'll give you an angle-dependent reflection coefficient at every single point. So that alone is an important message, because our entire industry today, our entire activity is on imaging condition 2. Yes. So, in this talk, we adopt imaging condition 3. We mean Claerbout imaging condition 3, since it has a unique benefit of clarity and meaning. What do you mean by clarity? It says, predict what a source and receiver would do at a coincident position in the Earth, and you get an answer at that point, is there structure or not? And because there's a physical experiment there, you can get an angle-dependent reflection coefficient with slight extensions, okay, that Professor Claerbout, Bob Stoll all benefited from. Okay, imaging condition 3 is what we're adopting in this presentation. It has two components, a prediction of the experiment, what would a given surface measurements, what would an experiment be if you had a source and receiver at depth? How do you arrange that? And the second part is the imaging conditions. Both of those ingredients have evolved. George Green, a little before John Claerbout, 1828, told us how, given surface measurements on a closed volume, you could predict what a measurement of a wave field would be inside that volume, assuming you know the material properties in the volume. Closed surface, those P and grad P dot N are measurements on the surface. The P is inside the volume. So that's a very important key guideline or for us in thinking about how to predict a measurement. The problem is, in exploration seismology, we only have measurements on the top of the surface. You can show that if you have an up wave, that if you take an anti-causal Green's function, let's go back here, that the great power of what George Green provided is that any Green's function that works in that, there's an infinite number of solutions for the Green's function. Any one of them will predict the field in the volume. If among the infinite number of choices, you pick the anti-causal one, and if you have an up wave, then all you need is measurements on top. The lower surface does not contribute. You can show that. What that leads to is pre-stack slope migration, where you see there's a sum over receivers, which brings the receiver down, and then a similar sum over sources, which brings the source down, having the entire imaging condition 3 experiment. Okay, now what if we have two-way waves? Why do we need two-way waves? We have issues with diving waves. We have, you want to migrate primaries and multiples. You have waves that are moving up and down in your volume. How are you going to arrange for measurements only on the upper surface to be sufficient? Anti-causal or causal or any combination of those will not work. For a two-way wave in the medium that you're predicting the experiment, you need to remove the contribution from the lower surface by choosing among the infinite choices of Green's function, a Green's function that, along with its normal derivative, vanishes at the lower surface. That we're going to call here G0DN, Dirichlet-Neumann. When you do that, you get this form, which tells you in a world where you have waves moving up and down, how do you predict the experiment at depth in terms of your data on the surface? Okay? The Green's functions there have information about the medium. If your medium is discontinuous, they have to know how to take you from where your surface measurements are to the point that you're predicting the receiver and then the source. But the data, which is in P, is there a pointer?
Yes.
Okay, thank you. Where's the point? Ah, that one. Oh, thank you. This P is your data. This is the experiment that you're predicting. So there are several papers. This is very recent, in fact. We've been so taken with imaging condition 2 for two-way waves, we forgot what John Claerbout taught us about imaging condition 3. This is just taking us back to that imaging condition which is unmatched for definitiveness and amplitude analysis. The other two don't have any comparison. So we want to, what we're going to do now is we're going to put data in that integral. We're going to put primaries, free surface multiples, internal multiples in that, and watch how that experiment gets predicted. You'll see a movie. One case, there'll just be a primary. We'll just watch that as that experiment gets predicted. You'll see how the original measured events become events in the new experiment. As you move to above and below the single reflector, then we'll do it for primaries and free surface multiple, then for primaries and internal multiple. And that will definitively answer whether multiples have anything to do with imaging and imaging inversion. If they contribute, you'll see. If they don't, you'll know. And will end that discussion. Then after we give you the answer to that, I'll tell you the answer right now. The surface data The surface measurements contribute to every experiment, every event in your surface data. Primaries, free surface, and internal multiple contribute to the predicted source and receiver experiment in the Earth. But once you make them coincident and time equals 0, then only primaries contribute. Whether you have multiples in or multiples removed, you get the same image. Okay? Multiples play no role in locating or inverting structure for discontinuous medium. If you have an accurate discontinuous medium. If you have a smooth medium, then every primary can be well located, every multiple will cause you a problem, an artifact. So for discontinuous media, multiples don't help, and for continuous media, you have to get rid of them. So then we'll ask, so what are people doing with calling migrating multiples? Okay, we'll answer that. Okay. So I'm giving you the, so this is 8 minutes left?
Mm-hmm.
Okay. In summary, no, I'm just kidding. So what we're going to do is we're going to follow the surface events as that experiment is predicted at different depths, and then we'll see. They'll be color-coded. In other words, if blue represents a primary that's measured, you'll see blue in terms of what it contributed to the experiment. Okay? For example, so here's case 1, just a single primary, and it's supposed to be a movie here.
Yeah, it's playing.
Oh, it is?
Yeah.
Oh, okay. I'm not seeing it yet. Okay. So that movie showed how that single primary, which is the only event, then gets. So what is the? How do you relate that original measured data to these different experiments? It's through that integral, that double integral, you know, with the Green's function that tells you how to get from one place to another. Now, so now what happens at the end is you have this is the experiment for all time, and on the right, when you ask for 0 time, that is the you get the R1 there from the primary. And similarly, the primary original, when brought, that experiment brought below the first reflector, gives you the experiment right below. And if you ask for time equals 0, that's what you get because you're right below. And you get minus R1, that reflection coefficient, because you have brought the experiment to that position. So here's we have a primary and a free surface multiple.
There you go. This one.
The movie's going, okay. So what you can see is both below and above the free surface multiple will contribute to the experiment above and below that reflector. But as soon as you say t equals 0, the original multiple is an event in that predicted experiment that's not at t equals 0. Words, think of a reflector. You have a source and receiver above it. You have a primary that came down. You have a free surface multiple. One of them has small time and one doesn't. When you ask for t equals 0, the multiple doesn't contribute. So when you do imaging, the multiple doesn't count. It counts for the experiment, but not for the image. So this is now an internal multiple. Same. Okay, that's just following. So for the internal multiple, the first primary is what contributes to the image above and below the first reflector. The second primary is what contributes to the image above and below the second reflector. Okay, end of that story. Free surface and internal multiples in a discontinuous accurate medium don't provide information. So that's what that says. And it says that if you use a smooth velocity, which we all do, you have to remove them. If you had a perfect discontinuous velocity and density, they don't help you. They don't hurt you. If you have a smooth and you don't remove them, they're going to hurt you. But they never help you. Okay? The conclusion is multiples never are involved in imaging and inversion. Inverse scattering series has the same conclusion. The multiple subseries are remove free surface and internal multiples, and after that, primaries are dealing with location and inversion. So what's all the activity with imaging with multiples? First of all, it's a misnomer. Nobody's imaging multiples. Okay? Nobody is, and nobody will. So I'll explain what that's all about. What is going on is the following. A multiple there, this multiple, if you predict it and you have a larger offset primary, the idea is to go back with the multiple, forward with the primary that you measured, and extract a primary, a shorter offset primary, sub-event of the multiple that you did not measure. Once you have that new primary, then you have more primaries than originally, and you go and migrate with more primaries. Okay? That is not migrating multiples. That event, that multiple event, that entity is not being migrated. Okay? It's being used to drag out a primary that you don't measure in terms of a multiple that you do and a primary within it that you do. There's a bit of circular reasoning. If you don't have that blue primary, you don't know that that's a multiple. In order to predict that black line as a multiple, you need to have those sub-events in your data. Clear? So what happens in practice? What I'm saying people who apply this are aware of. They can't predict the multiple because they only have one primary, the red one. So they take all the data in rather than predict the multiple. They just put the data in, and the data has the multiples, yes? And when the multiples deal with a primary, it does what is expected. It produces a primary that you didn't measure. But when the non-multiple in what you inserted enters the algorithm, it causes artifacts. Okay? So that's where that is. So here's an example from PGS. Here's imaging with primaries. We appreciate Lunden and Petronas for allowing for show rights. And here is what happened when PGS got additional primaries from extracting a primary from a multiple, yes? And you can see the clear benefit on the near surface, yes? They did not migrate a multiple, okay? So having more primaries is useful. So if you have the primaries that you measure and you get more primaries, how do you get them? You do more acquisition, yes, as we heard in the previous talk, or you do interpolation, or you use a multiple to try to drag out a sub-event primary that you didn't measure. All of those should be encouraged and looked at. Once you have as complete a set of primaries and multiples that you can, the next step is get rid of the multiples before you image, or you better have a discontinuous medium. Clear? So removing multiples has not lost any priority, and the removal of multiples is not a closed subject. Providing primaries isn't, and removing multiples. If you have an internal multiple that comes from a 2D Earth, which is interfering or proximal to a primary, and you want to remove it without touching a primary, there's no theory, let alone algorithm, that I know by anyone on Earth that can do that. That's not a closed subject. It's something we're looking at and progressing, but people think multiples is a closed subject. This is not the case. So one of the issues here is we've got enamored as a community with this run something backwards, run something forward, so we're going to run the multiples forward. you got to be careful. If it doesn't connect to Claerbout imaging condition 3, then you're away from physics. You could take a chicken, and make it walk backwards, and take a frying pan and make it walk forwards. Okay, put it in your car, make it work until they get together, and then you'll get some migrated fried chicken. Okay, whether you want to call it migration, that's your business, but it certainly has that. That has more reason to it than, say, when you put multiples in. Why? Because I can explain to you how the chicken got from the store to my house. I put it in the car, and George Green says, I understand. If you say I got multiples on the surface, and you have multiples in the earth, George Green is confused, because multiples don't satisfy a wave equation. So they don't know how Green's theorem is going to make that happen. So we welcome all methods that are including the use of multiples to get increased primaries. Being useful is not the same as being signal. Being useful to create a primary is not the same as being signal. There's lots of things that are useful. Money, a boat, a cable, no money, no primaries. Okay, so I guess we'll call money signal. You understand? So multiples can be useful for producing primaries, but at the end of the day, we image and invert with primaries. So here's a statement. The author gratefully acknowledges PGS for showing how multiples can be used to predict unrecorded primaries, and Luton, Malaysia, and Petronius for show rights. That's what's happening. It's the multiples being used. Okay? This acknowledgement was approved by PGS. This is what's happening. Okay? I appreciate the opportunity to speak here, and I'll try to answer any questions.
Yeah, so now the floor is open for any questions. We have 5 minutes. 3 minutes. Oh, 3 minutes.
Okay, Art, thanks for this nice presentation. Of course, you know I disagree.
All is well.
But that is, of course, good for the discussion.
Absolutely.
Yeah. Let me put it in this way, because I have only maybe 1 minute. Let me put it in this way. In practice, we will always have a non-complete data volume,
Yes.
and we will always have background noise.
Yes.
In that situation, we have to make money.
Yes.
And I can tell you, in that situation, the only way in the future to make money is making use of multiples.
Okay. In our history, between Hoos and us, we've always had respectful disagreements, and I can say from this side, we've always benefited from, and I look forward to further discussions.
Absolutely. So we
Thank
should
you for your
further
comments.
discuss the issue. To the organizers, I would like to say it would have been fantastic for the audience to have Art there and also somebody who images with multiples. That would have been great for the audience. Then we would have two things to go, and it would have been a great discussion. So maybe we could do next year.
Good idea.
Sure.
Okay, thanks, Art.
Thank you, Hoos.